The overall goal of this experiment is to quantify the dynamics of cortical actin by image correlation spectroscopy, following acquisition by total internal reflection structured illumination imaging, or TIRF-SIM.
This method can help answer key questions in the biophysical field, such as what role cortical actin flow has in regulating molecular interactions at the immunological synapse. The main advantage of the technique is that it combines nanometer scale resolution with live cell compatibility, allowing smaller scale processes to be observed and analyzed compared to conventional fluorescence microscopy techniques. Demonstrating this technique will be George Ashdown, a PhD student from my laboratory.
For a test sample, add 5 microliters of a 100 nanometer in diameter subdiffraction fluorescent microsphere stock solution to the surface of a fresh uncoated cover slip. Then, spread the microsphere solution over the cover slip with a pipette tip and allow it to dry. Add 200 microliters of mounting medium to the test cover slip to prepare for imaging. To begin, turn on the incubator for the stage heater of the TIRF-SIM system and fill the reservoir with distilled water to fully cover the base of the heating element. Let the water equilibrate to 37 degrees Celsius. Connect the heating collar to the objective lens and set it to 37 degrees Celsius. Then, secure the TIRF 488 compatible grading block in the light path of the microscope. To ensure that the correct optical path is engaged, switch the channel mode on the laser bed to the single position. Repeat this action for the fiber cable on the microscope stage. Expect to see an error in the software window if these steps are not performed. Having set the mode, lower the objective to the lowest Z-plane and place a drop of oil on it. Place the test sample cover slip with the fluorescent microspheres on the microscope stage. Then, select the Perfect Focus System, or PFS, function on the microscope body. Move the objective gradually up through the Z-plane and stop when the PFS button stops flashing, which indicates that the focal plane has been reached. On the control software, switch to Live View to image the microspheres on the screen. Make fine adjustments to the focus by using the PFS micromanipulator wheel. Observe uniform illumination with no out-of-focus fluorescence emission above the 75 nanometer evanescent wave. Finally, confirm structured illumination is achieved by observing a fluctuating illumination pattern from the fluorescent microsphere sample. For T-cell stimulation, coat the chambers of an 8-well cover slip with 200 microliters of anti-CD3 and anti-CD28 antibody mixture, and incubate the cover slip for 2 hours at 37 degrees Celsius. After washing the cover slip, as described in the text protocol, place it on the microscope stage, and then find the TIRF focal plane. Next, gently pipette 200 microliters of transfected T cells into one of the wells on the cover slip. Use epifluorescence to track the GFP actin transfected cells as they land on the cover slip. Once the cells have settled, change to live mode using the N-SIM pad and check that the cells on the monitor are in focus. To record a time course, open the ND acquisition window and select the Time tab. Then click Add and set the interval to no delay. Set the duration to 10 minutes. Finally, start recording the data by selecting Run Now in the ND acquisition window. To reconstruct the images, first open the analysis software containing the correct analysis module. Click on Applications, and then select the Show N-SIM window. set the illumination modulation contrast and high-resolution noise suppression to 1, and reconstruct the TURF SIM dataset to produce a complete SIM image. From the image status bar, confirm that the pixel size is 30 nanometers. And then export the data as TIFF files for stick analysis. After downloading and extracting the STIX MATLAB software package, open the script. Then, define the input parameters as outlined in the text protocol. For the immobile removal filter, in line 23, set the filtering parameter to moving average, and in line 24, use 21 as the move average parameter. To generate one vector map, set the temporal subregion in line 31 to the maximum number of frames, in this case 63. Then, in line 32, set the temporal shift to 1. In lines 33 through 35, enter the names of the output files, the titles of the output vector maps, and the output directory path. Then, define the format in which the vector map images should be saved, in this case, .png. In the MATLAB editor window, open the script Run 1 Channel Sticks and load the image series by running lines 1 through 23 of the script. Next, run lines 29 through 35 of Run 1 Channel Sticks to start the stick analysis. Follow the prompt and select a polygon to define a region of interest, or ROI, if desired. To display the vector maps, run lines 38 through 52. Then, run lines 53 through 72 to plot the velocity magnitude histogram. Shown here is a Jurkat T-cell expressing GFP-labeled F-actin, which was imaged with the TURF SIM protocol discussed in the text. 5 minutes after this cell was introduced onto a cover slip coated with anti-CD3 and anti-CD28 antibodies meant to stimulate the formation of immunological synapses, a time course was taken of it so that the molecular flow of F-actin could be visualized. Subsequent analysis of these data using the STIX program enabled the quantification of F-actin molecular flow, as depicted by this vector map corresponding to the boxed region of the cell on the left, which represents a portion of the synapse periphery. Further magnification of this map and T-cell subregion clarifies actin flow directionality and velocity, which can be determined from vector length as well as color code. Velocity data can also be plotted in a histogram, allowing for statistical analysis. Collectively, these results show that, in the immunological synapse, F-actin flows in a symmetrical fashion from the periphery towards the cell's center.
After watching this video, you should have a good idea of how to acquire TURF SIM data and analyze cortical actin dynamics using image correlation spectroscopy. Although this method can be used to gain insight into actin flow during T-cell migration, it can also be used in other systems where molecular flow is thought to be important, such as during cell migration.